Hi guys, great to see you again. I'd like to welcome each and every one of us to my channel of Honesty Sciences and Mathematics TV channel. I'd like to request us to kindly go to YouTube and search Honesty Sciences and Mathematics TV channel. Subscribe to our channel so that we can be discussing on various topics in mathematics, physics, chemistry, and biology, and other related topics. So for today, we're going to look at the concept of capacitance. And in our last discussion, which was basically an introduction part to the concept of capacitance, we had looked at this specific aspect as basically a device which stores electric charge. And we had said that the basic configuration of a capacitor consists of two conductors which are basically carrying equal but opposite charges. And of course, we had given an illustration that was showing different aspects of a capacitor and various electric field lines that were associated with that specific configuration. Now, I'm going just to give a rough illustration so that it can assist us, of course, advancing this specific concept of a parallel plate capacitors, our topic of discussion for today. Now, on the board, we are going to have three illustrations. I can perhaps name them for A, rather, this is for 1, 2, and 3. And these are going to assist us, of course, appreciate the different configurations and basically the electric field lines and how we can be able to, of course, quantify some of the aspects of the capacitance that we have learned and the concept of charge. So as we have said, of course, a capacitor basically consists of two conductors carrying equal but opposite charges. And from my figure 1, I've illustrated the charge for a positive plate and a negative plate and the separation distance, which I've indicated as D. Now, in this specific aspect, we are going to learn later that this concept of capacitance is going to heavily depend on some of the aspects, which are basically the geometrical aspects of this particular configuration, whereby we are going to consider the aspect of what we call the area or the surface of those particular capacitors. So in this particular case, of course, I'm also going to refer to the concept of charges. And it's essential for us to, of course, try to understand the field lines which are, of course, being portrayed insofar as the positive and negative charges are concerned. And we had mentioned earlier in our introduction to the concept of electrostatics that this basically charges are going to, if we have two particles for the positive and negative charges, which is analogous to this specific configuration, then therefore the electric field lines are going to originate from the positive charge and terminate on the negative charge. And that is the basic configuration that we are going to see here insofar as the electric field lines are concerned in this first design or first configuration for a capacitor. Now in this, if you try to visualize this part 1 from this specific sense, then using Gauss law and other related concepts that we have looked into, then it's going to assist us, of course, figure out how we can be able to interpret this basic configuration of a parallel plate capacitor, which is basically our topic of concern for today. Now, without going further, we had said that basically this specific device that we refer to as a capacitor acts as a storage device. And we're going to see that there are two states whereby we had mentioned the concept of charging. Just to use this one. We have two states for this capacitor whereby we can regard it as a charged and uncharged state. And in the charged state, this specific device is carrying some charges, where uncharged state it's of course devoid of those charges. Now, in either cases, for a charged and uncharged condition, we're going to see that basically the net charge on that capacitor is going to be quantitatively on a zero value, which means it's going to be zero whether it's either charged or not. Now, in this case, there's a relationship that has been developed whereby we see that for a charged capacitor, the positive charge is going to have a higher potential as compared to the negative charge. And that basically is going to create what we call a potential difference between the charged plates that we have given as delta V. And this delta V is usually treated as an absolute value, which is basically the magnitude of the potential difference or electrical potential difference between the plates. And there was a relationship between the charge and the potential difference of these specific plates that we had mentioned, and said that some experiments have shown that the charge that is stored in these capacitors is linearly proportional to the potential or electric potential difference, which basically gave us an idea that we can develop an equation to represent this specific relationship by giving it as a Q is linearly proportional to the potential difference but there's an inclusion of a proportionality constant, which is a positive value at this specific point that we're given as an initial C, which basically refers to the concept of capacitance. Now, therefore, this is the aspect that we're going to consider depending on different configurations. And perhaps for our discussion for today, that is going to be parallel plates, which are going to, of course, be illustrated as the figure 1 that I've given on the board above. So if we try to look at that specific concept, then I mentioned that this aspect of capacitance is measured using the values of farads, and I've given a conversion for farads as a ratio between the charge in coulombs against the potential difference in volts. So later on we discuss and say that there are different ways in which we can be able to symbolize this concept of capacitors. And in electronic circuits, we're going to have a general representation of capacitors for A, and then we're going to have a fixed capacitor that is going to be represented, of course, using this specific symbol. And this is in the case of polarized ones that we're going to encounter in some of our circuits, in other discussions that we're going to see under electricity and magnetism. But of essence for us is to try and see how this specific configuration is going to affect the nature of capacitance in this specific case. Now, in considering the concept of the field lines that I've mentioned, we have always depicted them as straight lines that are emanating from the positive to the negative charge. And in some cases, we're going to see that this is not always the situation whereby in an ideal form, we're going to have what we call edge effects. And these edge effects are realized due to the configuration of these capacitors, whereby some field lines are not going to be uniformly distributed as we are depicting them as such. But for the sake of quantifying them, then therefore, we're going to consider an ideal situation whereby these edge effects are ignored. And therefore, in this particular case, for us to consider an ideal situation, then therefore we accept that to compute these capacitances, then therefore we're going to use the concept of a Gauss law, which basically deals with the symmetry of particular bodies whenever we're trying to consider the surface area. Now, I've mentioned that we're going to consider the surface insofar as capacitance is concerned. This is because partly we're going to see that capacitance relies heavily on the configuration of a surface and perhaps the separation distance between them, which are the geometrical aspects of this specific configuration. Therefore, by Gauss law, then we're going to see that the electric field can be computed or perhaps calculated for a closed surface using these specific symbols. And we're given this specific formula saying that this is a vector quantity that can be given as, of course, the electric field being equivalent to the, perhaps, that's going to be this, the aspects of area and the electric field, which is going to be given as that on this specific surface. So that is going to be equivalent to the charge that is going to be enclosed. Therefore, this is Q enclosed over epsilon naught that is given. And this is the permittivity that we had mentioned in one of our videos, which is a constant. So therefore, in trying to consider this aspect of Gauss law, we're going to see that these two plates of illustration number 3, we can consider an area in this specific case for a Gaussian surface and try to see that if this particular section, we had said that we can be able to find the electric field of a curved surface through the use of those small squares. And in this case, we're going to consider an area in this specific configuration, basically that we are referred to as dA, for us to find an integral part of this specific illustration for the Gaussian law for this electric field. So in this case, we're going to just consider this area, and then basically this is going to form a Gaussian surface. And then this is the separation distance between the two plates, and therefore this product of electric field, we can give this area as, and give it an initial as A prime. And if we try to calculate this specific electric field, then it's going to be derivation of this EA prime, and then we're going to have the charge as Q enclosed over epsilon naught given as such. So in this particular respect, then therefore, this is going to give us what we refer to as the sigma A prime and over epsilon naught given as such, implying that the electric field is going to be given as epsilon. This is a reciprocal of epsilon, and this is this is a sigma over the reciprocal of epsilon, whereby the potential difference, which is going to be the change in V that we had given as a potential difference, is going to be the difference between the positive plate, which is V positive, and V negative. And if we consider our path of integration from the positive to the negative, and then therefore for this specific integral, we're going to have the change in potential difference. I'm going to use just use this surface. We're going to consider the potential difference between the positive and negative plate as a delta V, which is going to be V negative minus V positive from this specific integral. If our integral surface is going, or rather our integration path is going to run from the positive to the negative, then this is going to give us the potential difference, which is going to be basically the negative integral from negative to a positive of that e ds, and then we're going to have this one given as negative ed. So basically, this implies the division of our distance, and then we're going to have this one given as electric field ed, which has been given in this specific. I think we shouldn't assume this, so I'm just going to make a rectification from this specific point. I just intended to make this basically to be representing this specific Q over. So there's a representation here that I want to make a correction. This is for sigma, basically, and this I'm going to do away with this. I'd intended to do a substitution for sigma to represent Q over A prime in this particular case, but I'm just going to leave that so that it's not going to create for us a confusion from this specific point. So we're going to proceed from here. We had said that we can be able to, of course, find this specific electric field from this particular point, whereby we're going to have that formula that we're going to borrow from capacitors being represented as the ratio between charge and the absolute value of V given as such. So therefore, if you try to look at this specific formula, we have done an integral of this specific surface and said that the potential difference from the positive to the negative plate is going to be illustrated there using this, which is an integral that is going to be, this is a division of distance, so therefore it's going to result in D from that specific integral. And we had said that we're going to consider an absolute value for the potential difference in this particular case. So I'm going to use this space in trying to, of course, elaborate on this, so that we're going to see how we can be able to represent capacitance from this specific case. So I'm going to consider that one by trying to manipulate this formula and trying to create a specific part for that, where we're going to have a substitution for Q in this specific case, which is going to be represented as. So basically, this can be done through manipulation of these specific two formulas through a substitution. So we're going to have E being represented as Q. So I'm going to assume Q enclosed is equivalent to Q, just maintain it as that. So we're going to have this represented as Q over epsilon naught, and then we're going to have this one over division over. Now in this specific case as well, I'm going just to have this one represented as such. So if you try to do this one by making Q the subject, then therefore in this specific case we're going to have this represented as C, just going to have C and then delta V divided by the epsilon naught A. So if we try to look at this, of course, we had said that the change in potential difference can be represented as ED, and basically that we are going to consider the magnitude of that as a specific value. So we can be able also to do a substitution for that a second part. I'm just going to do away this so that it can assist us to have more space. So this is still a subject of A. So therefore, from this specific point, we're going to have A being represented as a C, E, D. And this is from this specific point. I've said I'm going to have it as just an absolute value divided by epsilon naught A. So if we try to look at that, we can be able to make C the subject of that formula. So therefore, C is going to be represented as this is going to be E, and then epsilon naught A divided by E D. Yes, so we're going to do a cancellation of this, and we're going to get these capacitors represented as epsilon naught A over D. So basically, that's how we're going to represent the capacitance of a parallel plate capacitor, whereby it's going to depend on the geometrical aspects of the area and the distance between the two plates as I've said. So basically, from this, we're going to have a conclusion that basically capacitance of a parallel plate capacitor depends on the extent of area. There are some cases whereby we're going to see that the plates might run infinitely, and in that specific case, we're going to consider the Gauss surface as I've illustrated, of course, from this specific aspect. So therefore, we're going to be, of course, keen on this specific substitution as we had done, of course, and take our time so that it's going to assist us in trying to find out the correct representation in this particular case. So next, we're going to look for a way in which we're going to represent capacitance of a cylindrical capacitor. And that, together with this, is going to assist us to create a contrast on how different, of course, configurations of capacitors can be represented and what is the difference between them. So that is it for now, guys. Bye. God bless you. Catch us in our next video.